Hello, Eastern Scholars. Welcome to another edition of Sharp Shorts, where we're going to answer the question, what's a solution? The simple statement would be it's an answer. But that's not quite the accurate chemistry moment. What a solution is just a method of making, of dissolving stuff, I guess is the best way to say it. A solution is a mixture. It's a physical property. It's a physical part of chemistry. And what you see here in the pictures is what it really is. Say I take this salt, sodium chloride, and dissolve it in water. I've then made a solution. Why would I do so? Because then it's easier to work. You can see what happens when something dissolves. Say a solid dissolves, like sodium chloride here. Sugar would do the same thing. Calcium chloride, any type of chemicals that would be able to dissolve in water, is you lose, not only you break the intermolecular bonds and you separate out sodium chloride molecules, but you also separate out some of the ions. And in a chemical reaction, say a single replacement or double replacement reaction, having those ions separated out so they are available to switch spots and make new compounds and have a chemical reaction is important. Oftentimes that won't happen with just mixing solids because they have no way of freeing up those ions to do an ionic reaction. Here is the basic definition in a chart that just shows you. While we will be very used to thinking of solutions as something dissolved in water, really a solution is a mixture of two or more substances in a single phase. So water, of course, being a universal solvent, is what most people are used to, and then things dissolve and it looks like liquid. And that's highly beneficial, but it's not the only thing. There are two parts to a solution. There is the solute. That is the thing that gets dissolved. In our last example, sodium chloride, or as you look at the charts here, a number of different things like like oxygen in the air, or carbon dioxide in soda pop, or acetic acid in making vinegar for your salads, or zinc in making brass metal. The thing that does the dissolving is called the solvent. Water 99% of the time is our solvent, because it dissolves most everything in varying degrees, of things that dissolve easily to things that don't dissolve very easily. But one of the ideas in solution chemistry is that like dissolves like, and since water is a polar substance and most everything, ionic bonds, polar covalent, most everything is polar, it will to varying degrees dissolve most everything. And so that's why people get used to thinking of solutions as just liquid things, but they're not. The gas we breathe is a solution. The soda pop you drink is liquid, but it's got more than just sugar and stuff in it. Brass, the solvent is copper. You dissolve zinc into copper. So the two key points there are, it can be any number of phases just as long as it looks uniform. You can see on the bottom some things that are solid, that look solid all the way through, that are mixtures, solutions. There's a whole bunch of liquid solutions and gas solutions there. And that the thing that gets dissolved is the solute, the thing that does the dissolving is the solvent. Why is this important? We talked about chemical reactions, but if you just think of pollution and acid rain, a couple pictures I have here, since the air is a solution, then by dissolving things in it, you can have reactions, and that's what occurs right there. The big point of this today is to look at how do we measure that concentration, and that is something that we determine is molarity. And that is signified by a capital M in chemistry, and what it is a measure of the moles of solute in the liters of solvent. Or if you think back to that picture that I had at the beginning with the salt dissolving in the water, it's really looking at those particles of sodium chloride that get dissolved, that separate out into molecules and ions in the space that they are given. And that's what liters is, a measure of space in the space that they are involved in. Okay, or encompassed in. The basic formula is molarity is moles divided by liters. Again, that's solute, so that's the stuff getting dissolved. Liters is the solvent, 99.9% of the time that's going to be water. I can take this 3 variable equation and I can rearrange it to solve for moles. I may need to do that if I want to know how many grams of, say, salt I want to dissolve in the water. I may have to calculate that to get a certain molarity, a certain concentration. And so I can rearrange that to say that if I want to find moles, then it's the molarity times the liters. I may need to calculate the volume and know how much water as a solvent I need to get to this concentration. So how much water am I using to dissolve, say, a given amount of sodium chloride? In which case, that's the moles of the solute divided by the molarity. So as you're working these problems, understand that you're going to get 2 of the 3 variables and just put them in the way they need to be. Remember, volume always has to be in liters, so it's given to you in milliliters or gallons or any type of thing, other type of measurement of volume. It has to be converted to liters. And anytime you hear grams, think moles. We should know now easily how to convert between moles and grams to do that. The last little bit here is how I read it. So if I had some 12 molar sulfuric acid, what that would mean is there are 12 moles in every 1 liter. Okay, let's try a few problems. I've got a few here listed, and I want to walk through them. What is the molarity of a solution with 38 grams of sodium chloride dissolved in 500 milliliters of water? Well, if we know, and let me see if I can get my pen working nicely, that molarity is moles per liter, then I have 2 things I need to do. I need to get the sodium chloride, 38 grams of sodium chloride, that's my solute, into moles. And I'm not going to run through that math because we should know how to do it. It's just dividing by the molar mass. If I do that, my number comes out to be 0.650 moles. Okay? That's going to be divided by my liters. Now I have 500 milliliters of water. That number I do need to get into liters, and again, I'm not going to actually do that math for you because we've done that since the beginning of the year. But if you remember to divide by 1,000, you've got 0.5000, getting our significant figures in there, liters. And then I just do that math, and 0.65 divided by 0.5 is 1.30, rounded to significant figures, molar, which is a capital M. Whoops, sorry, my pen just went a little goofy there. Okay, so that's our first problem. Let me scroll down a little bit so we can look at our second one. This is just, again, a permutation of what we're going to do. This says how many grams of calcium chloride I needed to make 1,500 milliliters of a 1.5 molar solution. So 1.5 is the concentration I want to make, and I need to know how many grams of calcium chloride to dissolve in my 1,500 milliliters of water. Now, as we rearrange the equation, then what we need to solve for is the moles, which is the molarity times the liters. And the reason I want to get the moles is so I can figure out grams from moles. Okay, so that just becomes 1.5, okay, times, and you should know 1,500 milliliters is 1.5, so that really gives me 2¼ moles. Okay. Now to get to grams, I'm going to have to, and I'm not going to show you the math because we know how to do this, but I'm going to have to multiply by the molar mass of calcium chloride, and so I'm going to have to add up the molar mass of calcium chloride. And your thing here is you should know your naming. That's 1 calcium and 2 chlorines. It comes out to be about 111 grams per mole. So if I change it to grams, then I will be at, sorry, I lost my pen cursor here a second. That's going to get me to sorry, having a little pen trouble. That's going to get me to 250 grams. Okay, if I convert 2.25 moles. I am leaving you some of this to do on your own, just because it's very old knowledge and you should be able to do it. Okay. Our last problem here, now that we are looking at it, is what volume of water in milliliters is needed to dissolve 225 grams. So I need to know, in this case, another permutation of the formula. I want to know how much water do I need in order to dissolve. I've got 225 grams of magnesium phosphate, and I want to make a 2.5 molar. That's my concentration, 2.5 moles per liter. And I want to know how much water in milliliters I'm going to have to measure my graduated cylinder. Again, the formula here then rearranges to liters is the moles divided by the molarity. Okay, so again, I'll kind of have to remember my formula for magnesium phosphate and write that out, because I have to get my grams converted into moles. So I've got to slide my little pen pad over a little bit. I need to get into moles, and to do that I need to take the grams and divide by the molar mass. And if I do so, then what I'm going to find out is that my moles are 0.8. Oops. Let's try this again with my pen quickly. Then my moles, I'll go down here. Then my moles become 0.859, checking my math, moles, which is 225 divided by the molar mass of magnesium phosphate. And then my molarity is 2.5. Okay. This will tell me my liters, which turns out to be 0.344. Okay. But it didn't ask me for liters, it wants to know milliliters. And again, on some of the math that I'm not going to quite do for you, because we should know how to do it by now, then that would be 344 milliliters. So in that case, I would head into the lab and I would measure out my 225 grams of magnesium phosphate, throw it in a beaker, take a graduated cylinder, measure out 344 milliliters, and throw that in and stir it up till everything was dissolved. At that point then I would have my 2.5 molar solution. Okay? So that is molarity and solutions. Our next video we'll talk about dilutions. What if we already have a concentrated solution and want to dilute it down and make it weaker? But until then, Scholar on, Eastview.